Okay, so it is my great pleasure to introduce Sam Staton, who's at Oxford University. And today will tell us about names and probabilities. Go ahead, Sam.
Thanks. Yeah. Thanks. Yeah. So I'm going to talk about names and probabilities. Thanks very much for this introduction, and thanks all for coming. Yeah, I'll sort of sum up what I'm going to say in a couple of minutes, and then obviously talk for a bit longer than that afterwards. So the key idea is that name generation is often probabilistic. I'll say some caveats to that in a second, but if it's probabilistic, then we can use the techniques that we know for probabilistic programs to look at name generation. Here's some pictures from probabilistic programs, but if you don't know about them, I'll tell you more about that as well. And then the key theorem could be described in this slogan: the off-the-shelf model for probabilistic programs is better for name generation than the off-the-shelf model for name generation. I'll explain what I mean by off-the-shelf and so on as well. And of course, I want to sort of make this a bit of a journey to talk you through what's name generation, what's probabilistic programming, and give you a bit of a perspective on the landscape. But this main theorem is in a paper that's just appeared last week in Popple. So if you wanted to see a very short version of this talk or a more detailed medium length version, you could watch the Popple videos as well, or look in the Popple paper, I suppose. Oh, the other thing is I already gave this talk in Cornell, so anyone was there, yeah, then, well, I don't know, maybe you knew I was giving the same talk or not, and yeah. Anyway, so that's the sort of a high level picture. Let me say a little bit more about programming with probabilities. Probabilistic programming is all about building statistical models by writing programs. Here's a very, very simple probabilistic program at the top. I draw X and Y from standard normal distributions. Here's the normal distribution, if you don't remember it from high school, it's bell curve. And then I add together X and Y. Now, if you know a little bit of statistics, you'll know that's the same as drawing from a normal distribution with variance 2, but you don't need to know that to do probabilistic programming. You can just write down this program here, adding X and Y together, and then plot the result, and you'll see this curve here. Right. So in general, we might write a very long and complicated program, borrowing bits of programs other people have written, and so you might not be able to do that sort of symbolic or simplification. Let's have another example. Maybe you want to draw from a normal distribution, but you don't know what precision to use or what standard deviation to use. And so a common thing to do is to take your precision from a gamma distribution. Here's a gamma distribution over here. I won't talk about sort of why you'd use a gamma distribution, but you can see it's on the positive reals. And so that gives you a precision, and then you use that as the parameter for your normal distribution. So here we draw X from a normal distribution with again mean 0, but well, the standard deviation is 1 over the square root of the precision. So that's why I put 1 over square root tau here. Okay, and then I could plot that, and I get this curve with slightly heavier tails. Sort of maybe intuitively, that's what you'd expect to happen if you didn't know what the standard deviation was. Now that has a name as well. That's the student t distribution. And back in the old days, people had to give names to all these distributions, but now you could just write a very complicated probabilistic program. We no longer need to give new names to all of them, all of these distributions, and you get a distribution out at the end. So yes, so it's very easy to build. I've shown 3-line examples, but very easy to build and combine complex distributions for statistics, for social science, for science, for machine learning using probabilistic programs, and to run things reasonably well in sort of prototype statistical models. These are, let's see, yeah, these are examples that you could run in Stan or Church or Web People or Anglican if you want to go away and have a go with these things. Yeah, that's a quick overview of probability, but I also want to talk about names. So let me give you another overview of names. Okay, so when we're talking about names, then we want to talk about things like these unique identifiers that appear in website, in URLs. This is the OWLs thing, right? Notice it needs a bit of updating, Jamie, since yeah, we need to be sure it's new, it's fresh, it's different from if there was another worldwide seminar, it would need to have a different unique identifier. We use names as well in memory, right? When we allocate a piece of memory, then we could think of the memory location as a name. In crypto as well, we'll use names, nonces, or something which behave in many ways similarly to names. And we can talk for a long time about philosophical concept of what a name is, but we like to think of pure names in this talk. And a pure name is something where the name doesn't tell you anything about where it comes from or what it means. It's just telling you what something is. In practice, pure names might be allocated by a centralized server, like 1, 2, 3, 4, 5. Each time you ask, you get the next number in the sequence. That could be done hierarchically or whatever. Or they could be generated randomly. And that's what I want to do today. I often say, in practice, it could be a combination of the two things. Like my own name, I think, is a mixture of a sort of centrally allocated surname and my first name, which is sort of pseudo-random because my parents came up with it for some reason. There's my name, Sam Staton. Yeah, there's a joke here because they've typed my surname wrong. I'm actually Sam Staton. And if you're at home in front of your computer with your sound off, you could try missing out the first T and see how that sounds. This was a badge from Flock, which was organized in Oxford. So maybe there's a message in there somehow. Anyway, so that's names. Yeah, so in this talk, we'll use random, we'll think of names as being random. And I'm going to use an abstraction. Normally names will be 128-bit integers, which are random enough to make sure that it's very, very, very unlikely you'll ever get a clash and you don't need to worry about it. But I'm going to use real numbers so that the chance of a clash, we can just say it's 0. Right? If I draw two numbers from a Gaussian distribution like this one here, I'll never get the same number twice. I could just say I never get the same number. And so I'll say, why can't we think of make a fresh name as draw something from a normal distribution? You could also use a different distribution, but I'll try and focus on the normal distribution just to keep things simple here. Okay, so yeah, so that's names. And I'm going to follow this passage where I start with name generation and then encode it into probabilistic programming by understanding name generation as random number generation. And then I'm going to encode that into a semantic model. That's, this is owls. So this is the S in owls to get a semantic model. And to make it all more interesting, I'm going to add higher order functions. That gives us a notion of abstraction or a notion of understanding what's going on and makes these things much more interesting. So I'm going to add higher order functions to name generation, to probabilistic programming. And then I need to add higher order functions to measure theory. Measure theory, as I'll explain, doesn't really support higher order functions. We've come up with Quasi-Borel spaces, which I'll explain, which do support higher order functions. And then putting all of that together, we'll end up with this full abstraction theorem. And I'm going to follow it in the reverse order, actually, the passage. Okay. So let's crack on now, I think, with talking about the model. I'm going to first talk about the semantic model, and then we're going to pass back and put everything into it. And it's a semantic model, not specifically about names. It's a semantic model of higher order probability. Okay. So probability, I want to explain by saying there's two different ways of looking at it. One is in terms of random elements, and one is in terms of measurable predicates. And I like to explain this in terms of darts. I realize it's like the worldwide logic seminar, or maybe darts is a British game. I don't know, maybe it's played everywhere. The pubs are closed at the moment anyway. So here's a dartboard, the game of darts. You throw pointy darts at the dartboard and see where you can land. And where you'll land is going to be random, even if you're really good at it. So we could describe where we're going to land in two ways, that randomness. We could say, random elements. What do I mean by that? Well, let's suppose you've got omega, the state of the whole universe. If we know what that is, maybe you need the history of the universe as well, I don't know. If you know everything, then where the dart's going to land is deterministic, given that information. Okay? I mean, to be a bit less philosophical, if you've got if you've got the seed of randomness, you can decide where the dart is going to land deterministically. It's just a function that, given the seed or given the state of the universe, tells you where it's going to land. And that's something probabilists use all the time, this notion of random element. So the space omega has a probability measure on it, but X, you don't really think of having a probability measure on it. It's just the place where the darts are going to land. The other perspective is to talk about measurable predicates, and that's sort of akin to saying, what's the chance of getting 20? So to score 20 in darts, you have to land in this region, that region, or I could get a double 10. Those are the ways I think of scoring 20 in darts. And so what I could do is to assign a probability to each measurable predicate. So we're going to talk about predicates, which are not functions from omega to x, but functions from x to 2. You can see the direction has changed now. And so chi is going to be a predicate that's measurable. I'm not going to allow all the functions from x to 2 to be measured. I'm just going to allow some of them. In particular, the probability of scoring 20 is going to be allowed. Okay. So that's random elements and measurable predicates. Now let me tell you about the sort of semantic models that are based on those two ideas and how to move back and forth between them. So let's start with on the right-hand side. So for measurable predicates, the notion of space is well known. It's called a measurable space, and that's a set equipped with a set of measurable predicates. I said not all the predicates need to be measurable, but you should have a class sigma of measurable predicates, and that should be closed under countable unions and complements so that you can talk about probability. On the other side, I'm going to talk about quasi-Borel spaces, and that's again a set, but instead of being equipped with a class of measurable predicates, it's equipped with a class of random elements. And those are, remember, functions from the source of randomness to the space. And again, we won't allow all of them typically, we'll just allow some of them. And they should also be closed under some conditions. For example, all the constant functions should be in there, and it should be closed under composition with measurable functions on the reals. And there's another sort of amalgamation condition as well that I'll skip over for now. So two notions of space, depending on how you orientate your notion of probability, really. But there's not sort of a conflict between these two ideas. You can move back and forth between them quite easily. And so let me tell you a bit about that. Let me first say how we interpret types and programs in both of these situations. So in both situations, types will be interpreted as sets with structure, either with a measurable space structure, measurable predicates, or a quasi-Borel space structure, the random elements. And programs should be functions that are morphisms. And what that means depends on which side you're on. So on the right-hand side, it means that if we take our function and then we compose with a measurable predicate in y in the codomain, we should get a measurable predicate by precomposing in the domain. On the quasi-Borel space side, what we want to say is that a morphism should be a map from x to y, a function from x to y, such that if we start with a random element in x and then we compose with f, we get a random element in y. Okay, so I'm not saying these two notions of space are the same, they're different, but they both support notions of morphism that perhaps look very symmetric. So let me say how to move back and forth between them now. Key example of a measurable space is the real numbers with the Borel sets. So the Borel sets are what you get from taking the open intervals and then making them into a measurable space. So closing under countable unions and complements. That sounds easy, but you have to go through a whole transfinite hierarchy to actually finish doing that. So that's a typical measurable space, the Borel sets. Now, given any measurable space, a set equipped with a collection of measurable predicates, you can look at the morphisms from the reals to x, and they will always form a quasi-Borel space. They'll satisfy the quasi-Borel axioms. So we can always move from a measurable space to a quasi-Borel space by looking at the maps out into the space from the reals. Let's go the other way around. The two-element set can be equipped with the structure of a quasi-Borel space by saying that the admissible random elements in 2 are exactly the Borel predicates, the predicates corresponding to Borel sets. In other words, open intervals and closed under countable unions and complements. So that gives us a quasi-Borel structure where we can say what the random elements are in the Booleans. They're just these measurable Borel predicates. And now using that, we can go from any quasi-Borel space to a measurable space by saying that the measurable predicates are just the maps from x to 2 from the quasi-Borel space. So by looking at maps into 2, we can go from quasi-Borel to measurable, and from looking at maps from R to the space, we can go from measurable to quasi-Borel. For anything simple, like the real numbers, Booleans, natural numbers, the plane, sequences of Booleans, even sequences of reals, it doesn't matter which one you use. The subcategories will be equivalent. It doesn't really matter whether you think of them as quasi-Borel spaces or as measurable spaces. So in other words, thinking of things in terms of random elements is the same as thinking of things in terms of measures. Where it gets different is when, in terms of types at least, is when you start looking at function types. So let's start on the right-hand side here. There's no measurable space of functions from the reals to 2. If I take all the measurable functions from R to 2, those are the Borel predicates, I can't turn that into a measurable space itself in such a way that it forms a Cartesian closed structure, if you know what that means. That was shown a long time ago by Aumann here. But there is a quasi-Borel space of these maps from R to 2. Okay, they're exactly the same maps, right? Because measurable is the same as quasi-Borel between these types, but we can put a quasi-Borel space structure on, and actually it's very easy to do that. What is a random element of the space of functions from R to 2? Well, to give a function from R to R to 2 is to give a function from R squared to 2. This is currying. And so we're just going to take those to be the Borel predicates on the plane formed by open rectangles and closed uncountable unions and complements. And those will be exactly the admissible random elements. We've already seen some Borel predicates on the plane in this dartboard example, the area in black, for example. Okay, and that's a union, by the way, of sort of three bits, isn't it? Okay, so that's a big advantage for us, for me anyway, of quasi-Borel spaces. Okay. Now let's switch and talk about probabilistic programming. And I'm going to show you what probabilistic programming is a little bit more, and then I'll talk about how to understand it in terms of quasi-Borel spaces. Okay, let's look at an example of probabilistic programming. We've seen two very, very short examples, but let's look at a slightly longer one. One of the key problems in statistics is regression. Given some data points, which function generated those points? And you see it's an inference problem over functions. We want to find a function that generated some points. So what you have to do in Bayesian statistics is start with a prior belief on what kinds of functions you might be talking about. So here's a prior that I'm going to use, and I'm going to show you the regression result in a minute. Here's the prior, it's on linear functions. So this is a little program that describes a random linear function. So what we do, we sample the slope, which should be normally distributed. Let's put the mean as 0, the standard deviation quite big too. The base point, the intercepts of the linear function, again, normally distributed. And then I form this function Sx plus b, and I call that g. Okay? So Sx plus b is g, it's a function. And so every time I call this function, random linear, it gives me a different function g. I called it 1,000 times and I plotted the different results I got. You can see, because the mean is 0, concentrated around here, but they could go anywhere. Yeah, what's the type of this function? Well, it's a distribution on functions from reals to reals. Okay, so random linear describes a distribution on functions from reals to reals. Yeah, that's what I said there. And we can think of it as coming from a random element. So what is our source of randomness in this case? It doesn't have to be the history of the universe. It's just two numbers. It's the S and the B. And given S and B, we can determine a linear function Sx plus b. So this little function here, which is the random element describing this random function, is just the function that takes S and B and returns the function Sx plus b. But in general, we might have another kind of type or another space, and we can talk about the probability measures coming from random elements inside that space. Yeah, so that's a random linear function. Then what we would do is to, and I won't show you the program that does this, but in a probabilistic programming system, you'd be able to incorporate observations. So you'd use Bayes' law, which starts from a prior belief, right? This is this very uninformative prior. I really don't know what kind of function. I know it was linear, but that's all I know. And then I say, okay, now I've got my data and I want to find out what's the posterior belief about what the function looks like. And so I ran my probabilistic programming language and I got back this distribution. I think this is again 1,000 lines, and you can see it's a nice distribution over which line probably generated these data points. Okay. So this is all dealing with probability distributions on function spaces. So function spaces are really important here already, but let's crank it up a bit. I'm going to think about a function. I won't show you again the definition, but a function called piecewise. Now, piecewise takes a random function and gives back another random function. And what it does is to chop up the x-axis into bits randomly, pick some random change points, and then pick a different random function from its argument to fill in the different bits. So if I give it a random linear, piecewise is going to give me a random piecewise linear function, like the ones we've got here. So I again ran the Bayesian regression, the Bayesian inference problem, and my posterior distribution now looks something like this. You can see it wasn't sure where the change point should be, but it's almost certain it should be between 3 and 4. Perhaps actually there wasn't a change point and it was just a straight line. I don't know how well that's coming through across Zoom with the bandwidth and stuff. Okay, but I've used as my prior now piecewise random linear. So piecewise is a second order random function. I can even make it more interesting, right? So let's start with random constant. And that's just it's slightly simpler actually than a linear function because it just has a constant. So these constant functions are just constant functions. They're not very interesting. But if I call piecewise with random constant, I get a random piecewise constant function, which is much more interesting, right? It's these step functions. Here they're all going up, but they could just as well go down. Okay, so I ran the Bayesian inference problem again, and it found me all of these piecewise random constant functions to fit the points. We could carry on, right? We could do random cubics, we could do random logistics or random Brownian motion, and then do piecewise versions of those, piecewise Brownian motion or piecewise random cubics, and just composing all of these things very nicely together using the higher order functions. Okay, so that's what I want to say about probabilistic programming and where the higher order functions I think really play a fundamental and important role there.
Sam, sorry to interrupt. There's a question by Jamie Vickery.
Oh, hi, Jamie.
Hi. My question has been introduced very grandly. I mean, it's not a very grand question. Could you go back to the first example that you had with the linear, just a few slides back?
Yeah.
So maybe forwards to So these points. So I understand what you're doing here, but of course these points aren't collinear. So why? I mean, one might say, well, the system would just fail because it would say, well, these points are collinear, so it's not consistent with any possible. So why is it operating in this way instead? I understand that this is meaningful as well, but what if, I mean, in some more complicated scenario, you might actually want it to tell you, actually, no, this could not be, this distribution could not possibly have arisen from any function of that.
Yep, you're absolutely right. So two answers, I suppose. One is, I mean, I didn't show you the actual problem or Bayesian inference model, but what is inside it is actually first of all, I say that the prior is this random linear functions, but then I also say that these observations are noisy observations about the function.
Nice.
In other words, what's happened is I've got a point here, and then I'm going to draw from a Gaussian again, and I'm going to observe that point there is the value of the Gaussian that I drew.
Would the alternative be possible then, if you did actually want it to say, suppose you knew that there was no noise in your observation, you want it to say, no, this is not consistent. Would that be by adjusting?
Yeah, so that's not possible in quite a few languages like Church and Stan, I think. It's called Kriging. I think that's how you pronounce it in Bayesian, in Gaussian process theory. We've just actually submitted a paper about how to understand that semantically as well. This kind of exact constraint where you want to say, I know that that's exactly what it is, and maybe say that after the fact. Yeah, so it's a very timely question for me, having just written a paper about it. Yeah, yeah. I mean, the other thing is, maybe you're used to knowing the line of best fit or something like that, and turns out with Gaussians, that the most likely line will actually be the least squares best fit. But in general, that's just for linear regression. Yeah. Okay. Any more questions? Yeah. Oh, just I mean, I said that these points, I said that there were noisy observations about the data point. You could say, I don't know what the amount of noise is, and draw that from a gamma distribution. So you very quickly build quite fancy hierarchical distributions, and it all works fine.
I did have, since you're asking, I did have one other question from a couple of slides before, maybe. It was, forwards, maybe forward 3. Oh, you're going quite fast. Forwards, oh no, back from here. Sorry, maybe back 3, maybe. So here, I was a bit confused. You're saying R is isomorphic to some Borel space of, some other Borel space. What's this isomorphism here?
Oh, the reals are, but the reals are isomorphic to the plane in measure theory.
Oh, I see.
Yeah, I know that's, if you're topological, that's ridiculous. Yeah. So
does that play, is that playing is this just like a convenience here, or is it fundamental for the?
It's fundamental in the in the definition of quasi-Borel space, because I've just picked there to be one source of randomness throughout. So quasi-topological spaces use
then that you just use R as a universal.
Yeah, exactly. Yeah.
Thanks.
Okay, is there any other questions just now? I think we've just got to the end.
No, that's it for now, Sam.
Okay, I've lost. I think I just finished talking about probabilistic. Yes, that's right. Yeah. Okay. Let me talk now about name generation. So in a way, I'm going to change tack altogether for a few minutes. I think Andy's here, actually. I'm going to talk about the new calculus, which is a calculus for name generation and has higher order functions in it. So it's just perfect for looking at the kinds of things that I wanted to look at. The types of it are Booleans, names, and functions. Functions from names to names, names to bools, names to names to names, and so on. And the new calculus, as I said, it's sort of like a lambda calculus in that they introduced a new symbol as well as a lambda abstraction. And new AM means generate a fresh name and bind it to A in M. Well, that's what intuitively means. So all we have are the lambda abstraction, function application, applying this new, and then equality. We can ask, are two names equal? That's sort of the basics that you need to have to talk about these concepts. So if I generate a new name and then I say, is it equal to B, where B is another name that's around, the answer is always going to be false. It will always be different. I'm just giving these axioms intuitively, and then I'll talk about how to justify them in a second. These axioms are old due to Andy Pitts and Ian Stark, or perhaps some of them even older, I suppose. The second axiom, it says, if I generate a new name and then I call a function and I actually don't use that name ever again, it's the same as just calling a function without using the name. And the third axiom says, if I generate two new names, A and B, and then I call F with A and B, it's the same as generating the names in the other way, in the other order, and then calling F with the two names. Now, if you've got a centralized server that's spitting out names as numbers, 1, 2, 3, 4, 5, 6, 7, 8, then these equations won't be sort of totally obvious, because when I generate a new name and then forget it, something's changed, right? Because that number will never appear again, and I can detect perhaps that it's happened because I can look at the numbers that are coming out. Similarly, if I generate A and then generate B and then call F with A and B, it's the same. Well, let me write that like an alpha convert and say generate A and then generate B and then call F with B and A the other way round. Then if we're talking about names as numbers generated in step one by a central server, these things will be different, because I'll either get 2 and then 3, or I'll get 3 and then 2. But observationally, if these are pure names, we shouldn't be able to tell the difference between these programs. And it turns out, if you just look at ground types, these equations are pretty much the only equations you need to talk about to completely describe what's going on with name generation. So let's make it more interesting and talk a little bit about slightly higher types. But before I do that, let me say a little bit about probability, just a hint. So remember, I want to say that new AM means not generate a fresh name, well, maybe generate a fresh name, but sample from a Gaussian distribution, from a normal distribution, a real number. And then, as I said, if I generate a new name, it's going to be, if I randomly draw from a Gaussian, it's going to be different from any other real number that I'm thinking of. And this equation here at the bottom, well, I can think now, because, let me step back. If I'm talking about sampling, sampling is all about, in probabilistic programming, all about Monte Carlo simulations. Monte Carlo simulations are ways of computing integrals. So in other words, this new is a bit like an integration operation. And so if I just squint at this equation here and rewrite it using integrals instead of the new symbol, I see this equation here. FAB with respect to B and then with respect to A is the same as integrating FAB with respect to A and then with respect to B, where these integrals are over the normal distribution. And this is a fact about integration, which is called Fabini's theorem. Okay, but let's start to add in some higher types. So here's a little program which turns out to be really important, I think. Generate a new name and then return a function which takes an argument B and tests whether A is equal to B. Now, if you're familiar with programming and compilers, you could describe the outcome of sort of evaluating this as a closure, which is to say a little program, lambda B, A equals B, together with an environment that says what A stands for. So when we create the closure, we generate the name A, and let's do it randomly. We get this big long integer, and so this is our closure here. I want to take that program and I want to compare it to this program here, lambda b false. This program will always return false. And I want to say, are these the same? It turns out they are the same. The only way to tell the difference would be to pass in this number A. If I pass in this number A to the left-hand side, I'll get back true. If I pass it into the right-hand side, I'll get back false. But this number A is wrapped up inside the closure, and it's so big and so random, no one can possibly guess it. So it's private, it's effectively private, and I can't tell the difference between these two programs. They're the same. So to prove that they're the same, would take a little bit of effort in terms of reasoning about privacy and so on. I'm going to show that it follows immediately in the model of probabilistic programming. Let's look at some other examples though. So that's sort of the primordial example, but let's look at some other examples. And these are all examples I think that Ian and Andy looked at and dealt with and proved back then. Second example, if I generate a new name, and this is a function that returns a name now, and then I take an argument B and forget it and just return A. Okay? So I'm always going to return A. So what's going to happen is I run this little bit of code, I get back a closure which has wrapped inside it this random number that gets allocated A, and then every time I call the function, I'll return the same number, 130, blah, 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 blah. On the right-hand side, what I've got is the function that takes an argument and then generates a new name. Every time I call the function on the right-hand side, I'm going to generate a new name. This is a call by value semantics. I mean, there are other ways of understanding name generation, but I think this is the prevailing one, really. Okay. So the right-hand thing obviously looks different, but that doesn't mean it's different. So to understand why they're different, we need to think about what happens when we run them. So when I run this one, I get back the same number each time I call this closure. Each time I call this closure, I get back a different random number. So they're totally different, very, very different. Oh, I should say, I initially was saying they had types like this. Now I've put the monad in. For those of you who know about monads, if you don't know about monads, well, you should, but let's leave it there. Yeah, so one of the beautiful things about this program here is it's equivalent to this one. And this is, I think, really interesting. So here we generate two new names, A and C, and then we say, take an argument, just as before. If B is equal to C, the second name we generated, then we return C. Otherwise, we return A. Now, it turns out there's no way of getting C out of this program, because to get C out, you would have to pass C in, right? Because the only way to get C out is to get a true on B equals C. And so to get that, you would need B to be C. So you'd need to know what C was. So if you don't know what C is, you can't get C out. So you can never get C out. So these two programs are the same. I just argued informally, but again, you can prove that formally, and it is true in the probabilistic model. What's I think really subtle and beautiful is that it's different from this program here. So here, what I've done is I say, take an argument B. If B is equal to A, the first name I generated, then return C, otherwise return A. Now I can always get out of this program A and C. How do I do that? Well, I first make up a name. I call the function once, right? That name will not be the same as A, right? Because I just made it up and I didn't know what A was. But now the function is going to return A. So now I've got A. And now I call the function again with A, and it comes back in. Is B equal to A? Yes. So I'm going to return C. So you see that by calling the function twice, we can get back C. We can extract C from this function. So C is not private in this function, although you have to call the function twice to get it out. And again, this distinction is true in the probabilistic model immediately. Okay, so yeah, I think that's what I wanted to say about new calculus, and there's a lot more to say, I think, but that's what I wanted to say for now, purely about the new calculus. Yeah, and so what I'm going to do now, unless anyone wants to interrupt with a question, is to pass back down through probabilistic programming to quasi-Borel spaces and get this theorem which says that quasi-Borel spaces are fully abstract for new calculus at first order. In other words, they can prove all of those equations and inequations. Oh, by the way, I mean, when I say first order, I mean that functions only take ground type booleans and names as arguments. We're not going to consider functions that take functions as arguments. That would violate, in general, this full abstraction property. Remember, full abstraction means that contextual equivalence, observational equivalence, coincides with equality in the model. Okay, so yeah, so let me talk a bit. I mean, I'm not going to sort of go through the proof because it's a very difficult proof, but let me talk about the ideas in the proof and the sort of conceptual ideas there. So let's look at these two programs again. Remember, these two programs are the same. The first one generates a new name and then takes an argument and asks whether A is equal to B. And the answer will always be false because you can't guess what A is. No way of getting A out of this function. So these two programs behave the same. It's sort of privacy property or a secrecy property. The name A is secret. What could distinguish them? Well, if we had a function x, now x is a second order function, which takes a function as an argument and tests whether there's any possible argument that could possibly make the thing return true. So it takes an f, it searches or whatever, finds an a such that fa will be true. And if it can do that, it's true. You know, this is x stands for exists. If it can do it, it's true. If it cannot do it at all, it returns false. So if I apply x to the left-hand side, there is an argument that would make this function return true, namely 13038, blah, 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 blah. I don't know what it is, but if I'm existentially quantifying, then I could find it. Whereas there is no argument that would make the right-hand side return true. So the x of this would be false. So if I had this second order function x in my language, I could tell the difference between these two things. Now, x is allowed in the nominal sets model. I could add x to my language and still give a denotational semantics to the new calculus in nominal sets. So nominal sets, sorry, are the semantic model roughly that Pitts and Stark were working with. I mean, they came afterwards, but I think it's fair to say it's roughly the model that Pitts and Stark were working with. Very, very simple and beautiful model for new calculus and for name generation generally. But, well, maybe it's a positive thing, I don't know. X is allowed in the nominal sets model. X is not allowed in quasi-Borel spaces. So this function x is not allowed. So we can't, at least, this doesn't show that we can't distinguish these programs, but it shows, it's a hint, because it shows that the way of distinguishing them in the nominal sets model doesn't work in quasi-Borel spaces. Let me give you a hint why. Suppose we had x, this function x, which tells you whether there's an argument that gives back true. Then what I could do is define a projection function that takes a function from r squared to 2, in other words, a region of the plane, right, predicate on the plane, and projects it down to the x-axis. We'll draw a picture here. Projects it down to the x-axis. So I could define this function here, and what it does is it takes a predicate on the plane and projects it down to the x-axis. Now, I want to think in the quasi-Borel space model of, well, I do think of functions from r squared to 2 as exactly the Borel sets, the sets built from countable unions and complements of open rectangles. And it turns out that the projection of a Borel set is not a Borel set in general. So if I have a Borel set up here and I project it down, it's not in general a Borel set. That might not be obvious. I think it was not obvious to Lebesgue, who made a mistake about this. But it's true that there are Borel regions of the plane where when we project down, we don't get a Borel subset of the line. So in other words, that means that we can't have x, because if we had x, we could define this projection function. Now, that's not enough to conclude full abstraction, because I've only shown that we can't distinguish these programs using x. To show that we can't distinguish these programs at all, I need to consider all the second order functions of this type, right? All the second order functions that take a predicate and give back predicates on predicates. And it turns out that this is a class of well-known functions in descriptive set theory called Borel on Borel sets. So we need to show that these programs are equal. We need to consider all the morphisms. So x had this type. It took a function and said true or false. It does that exist an argument that makes it true. We need to consider all of these. So we do that by characterizing or understanding characterization of the Borel on Borel sets. So these are, what does that mean? Well, if I have a function here, if I have a function capital F, it needs to be a morphism between quasi-Borel spaces. In other words, whenever I have a measurable rectangle and I compose with F, I should get back a measurable area of the line. Okay, so that's what a Borel on Borel set is. There's some quantification going on there. And as I said, it's a concept from descriptive set theory. So we called in our first, our first and last co-authors are descriptive set theorists, And so we called them in to come and help with this problem. And they got really into it. And yeah, I think we got some interesting insight into there as well. Okay, so by understanding the Borel and Borel sets, we're able to show that there is no function that distinguishes these two programs. Okay, so that shows you how we prove that these two programs are equal using Borel and Borel sets and characterizing all the functions like this. But you know, I want to show that all programs are equal. All programs. I want to show that programs that are observation equivalent if and only if they're equal in probability distributions. So here's a little outline. I should probably start wrapping up now, but we prove this privacy law that says these two programs are equal. And then we take arbitrary programs and we put them into sort of beta eta normal form. And then we use this privacy law and some other translations of the reals and some invariants of the normal distribution under some symmetries to normalize further. So for example, let's come back to those two programs that I talked about. Yep. This program here, remember, this is the one where we can't get C out of it. When we put it into normal form, it will end up like the thing on the right-hand side. Whereas the program here, the second program, well, that's already in normal form. Yeah, so then we have a normal form modulo privacy, and then we show that's complete. And we used then a lemma from Ian Stark, or theorem from Ian Stark's thesis characterizing full abstraction at first order. I thought I would just finish by saying a little bit about how names are used in statistics already. So we talked about regression already as a typical kind of statistical problem. Another problem is clustering. I did a bit of work about hate on Twitter towards UK politicians. This was before, this was a couple of years ago when the 2017 election, I think. Each point here is a UK politician, and maybe we want to group them into groups to think about what sort of people are around in the political sphere. And you can maybe squint at it and see some groups. I think I've drawn some here, yeah, right. So these guys down here didn't get many votes, but generated quite a lot of hate. So maybe they're sort of very active or noisy, but not very not actually getting elected. These guys over here probably don't engage with social media. These guys here are sort of really in the melee for winning seats. And then these outliers over here, this is a log scale. These guys are getting loads and loads of hate, loads of abuse. We could ask, what should we call the clusters? I've colored them red, blue, and green and yellow, and I've given little narratives to how I sort of squinted at it and saw the clusters, and just afterwards came up with these little stories. But we want to automatically, we want to give them names. And I mean names in the sense of names that we've been talking about just now. Now it's quite subtle because, here's another example, is a Twitter timeline for someone, I've forgotten who, but these are the hate events that they experienced. And we can see they came in two clusters, right? There's a sudden burst of loads of people jumping on them at this point. I think this is over a month. And then there was another little sort of gradual amount of hate building up here, maybe in the lead up to the election or something. And so the clusters now look like these sort of mixture of normal distributions. So what do I want to say? Yes. So crucial thing about naming the clusters is that you need to be, everything's symmetric in what you name them. And you can see I stopped the analysis a little bit early, and it's wondering about whether to call these guys this guy here the red cluster, and this guy here the blue cluster, or this guy here the red cluster and this guy here the blue cluster. And so you're potentially going to waste a lot of effort in your inference by this crucial property of names, which is that they are symmetric, exchangeable. So understanding the way that names behave is really, really important, even in inference in this way. Now the Dirichlet process, well, here I've got two clusters. The Dirichlet process starts by saying, I don't know how many clusters there are, and I'm going to find that. Okay. So in the Dirichlet process, it takes an argument, which is a distribution over cluster names, basically. And so what statisticians tend to do is to use a normal distribution for this. They say, let's name the clusters by a number between minus infinity and infinity. Or, if we want to do colors, let's name the clusters by some point in this color plane. And then they'll use that number that's given to the cluster as the name of the cluster. What happened in probabilistic programming is that these guys said, well, actually, let's just use GenSim. Let's just generate a fresh name for each cluster. GenSim is a probabilistic program. And so we can treat it as a distribution and pass it to the Dirichlet process, which now gives us a distribution over names. So so we can already, so people were already starting to use GenSim and names as a crucial ingredient of probabilistic models, I think. So maybe OWLs, or at least logic and semantics, suggesting new ideas like this for statistics. And that's where I wanted to get to. So thank you very much.
Thanks a lot, Sam. I'm gonna unmute everyone so that we can thank you. Let me see if I can do that. Okay, let's thank Sam for his talk. Okay, and now I'm back to muting everyone. Sam, I had to mute you as well, so if you can unmute yourself, that would be great. There are a few questions. Paulo Perrone, do you want to go ahead?
Yes, please. There's something that I don't understand, I think, about new calculus. Namely, if you could go back, for example, to the slide where you compare two programs, the one that reveals A and the one that doesn't. By the way, Sam, I think you're muted.
Sorry, my screen share has gone, hasn't it?
No, it's showing. It's showing. We see your last slide, Sam. Not, yeah, the conclusion slide.
Oh, really? Is it sharing this?
Yeah.
Yeah.
Okay. Is it sharing Zoom as well, or just this?
No, it's sharing the whole screen, Sam. So in case you wanna stop sharing and resharing.
Sorry, yes, go ahead. This one, yeah.
Yes. So my question is, okay, you say that these two programs are different, and because using the second one, we can get A by running the program twice. Is this correct? Have I
You can get A by running the program once, and C by running the program twice.
And C by running the yeah, okay. So my question is, if we run the program the second time, wouldn't C be generated newly? So wouldn't C be different in principle?
Yeah. I'm being a bit casual when I say run the program twice. When I run the program, it gives me back this closure. And now this closure is something that's a value. This program is not a value. So when I run the program, I get back a value, which is this closure, which is this function, which has built into it the two names.
Oh, I see.
Yeah.
Okay.
So those two names are now built into the closure, and they're the things that are private, or potentially private until they're exposed.
I see. Okay. So the things generated by the first news are staying there. Okay.
Yeah.
Okay.
Yeah.
Now it's clear. Thank you.
Yeah. This is a sort of typical call by value semantics for.
Okay. Thank you.
Okay. The next question is Andy Pitts.
Hi, Sam.
Hi, Andy.
Hi. So the great thing about semantics is that you can apply it to lots of different programming languages. And so the new calculus that Ian and I invented, well, we didn't actually invent it. We stole it from Matthew Hennessy and some other people. But,
Was that right?
Oh, yeah. No, it's just a subset of ML, really, anyway. But
yeah, sure.
What I was going to say is that it's not the only language with locally scoped names. There's another very interesting one by Martin Odersky called it a new calculus as well.
Yeah.
I wonder whether you'd thought about using Quasi to model that.
Yeah.
I mean, the interesting thing is that I think I had a student, Stefan Lersch, well, actually it was Lynn Winskall's student, but we wrote a paper where the existential quantification thing comes up because there's a sort of Plotkin-like result, that it's roughly speaking the only thing that's stopping full abstraction for the new calculus in nominal Scott domains.
Oh, is that already in Stefan's
thesis?
thesis?
Remember the fact that the Dursky new calculus is quite well behaved in some ways. I wonder whether Borel spaces might give quite a nice model of it.
Right. Sorry, is the fact about exists in Stefan's thesis then about?
We have a JAA CM paper from about
okay.
2015 with that. It's called Full Abstraction for Nominal Scott Domains.
Okay, thanks. Yeah. Oh, we should have cited that. Yeah, thanks. Yeah, no,
well, but it's about a Dursky new. It's not about dynamically allocated names. So,
right.
so it's about a different language, right?
Yeah,
so you shouldn't have cited it.
Well, if you exists playing a crucial role, but so with the Dursky, I guess a Dursky is called by name. So if Dursky new is called by name, so you would have to.
Yeah, it's a little bit different from that. It's a very strange conception of local naming where the scope goes inwards rather than outwards. So it's very hard, I think, for people to understand what it is. But it is, in some sense, more fundamental because you get GenSim by doing you can do a continuation passing style translation to get GemSim out of a Dursky. So in some sense, it's more fundamental. I
always thought of it as called by name. Did you not think of it in that way?
Well, it is called by name, but the names are also doing something a bit weird as well, independently of the function calling strategy.
So my thought was that because I thought it would have a semantics in category of algebras for the so restriction structures.
Oh, it does, yes. But I was just wondering whether Quasi Borel things would be
so that's what I was
abstract model and then
yeah. So then you would need to look at perhaps at algebras for the probability monad. In other words, sort of convex spaces.
Yeah,
exactly. So that I haven't thought about that, but it could be interesting.
Yeah. Okay, just a thought.
Yeah, no, that's right. Yeah, thanks. And because actually we don't understand those even for first order for ground, for measurable spaces. We don't understand algebras for the Giry monad very well, I think. So it could be a way of understanding those a bit better.
Okay, there's another question I'm going to read from the chat, and then there's at least one more question I'll let the person ask. So there's a question from the chat from Will Smith. If second order functions aren't valid in QBS, does that mean that probabilistic programming languages with hard constraints, hard observations, aren't either?
So, sorry, second order functions are there. It's just that new calculus is not fully abstract at higher types in quasi-Borel spaces. Just because having higher order functions around allows you to inspect things a little bit more. I could say a bit more, but quasi-Borel spaces are fine for probabilistic programming at higher types. Well, they're fine. They're not fully abstract, as most models aren't at higher types, but they're fine.
Okay, there's a second part to the question, which I think was sort of clarifying the first. You could just sample the name and condition on having drawn the right name. I'm not quite sure exactly how this links to the constraints, but hopefully you answered the question.
Yeah, I see. I mean, it's a slide sharing. I mean, this A equals B is not it's not really a condition in the sense of a Gaussian sort of Bayesian update. I don't think of it in that way. So, but and I don't think you could or should. But yeah, okay, it's an interesting question.
Yeah, thanks, Sam. Jamie, do you want to go ahead?
Yeah, thanks. So maybe you mentioned this, but I'm unclear on this point. Do you have a way to decide syntactically if two programs have got the same quasi-Borel behavior?
Yeah. So yes. So for first order, remember there's no recursion in. Well, maybe you don't remember because I didn't say it, but there's no recursion in this new calculus that we're looking at. So yeah, at first order, and actually we couldn't find a reference for this. You can put things into a normal form and then just compare the normal forms. So that's how our proof goes.
So that's a normal form that you're using off the shelf.
No, we sort of came up with it. I imagine that people knew it 20 years ago. I didn't know.
But now but this point that there's no recursion, then could you say more about that? I mean,
Oh, I just mean that when you have recursion around, then you can't find normal forms because, well, typically you
Okay, but it would be nice to be able to reason probabilistically about programs with recursion. So could you just say a bit more about that limitation in the context of?
Gosh, yeah. Okay. Yeah. Yeah. I mean, this is okay. That's a separate topic, really. But yeah, we can add recursion in. So one thing we did a few years ago in another paper was to talk about quasi-Borel CPOs. We call them omega quasi-Borel spaces, I think. And so there we have a set X which has an omega CPO structure, so that you can model recursion and solving recursive domain equations. So it's sort of a hybrid of a omega CPO for all recursion, and then a quasi-Borel structure, and that just works really, really straightforwardly, actually.
Mm-hmm.
Yeah, I mean, yeah, I don't know if I should say this publicly. I'm not that sure that CPOs are in general the best way to deal with recursion, but it worked.
Okay, thanks.
Okay, thanks, Sam. I think that's it for questions. So I'll stop the recording now before we move to the informal part of the meeting.